All right, good evening. And welcome to a very exciting special session. Today we will focus on Student and Startup Innovation Challenge. Innovation Challenge. My name is Rosalia Baker, and I'm a Field CTO, Packaging Technologies with Rapidus. And I have the great pleasure to co-chair this session together with Farhang Yazdani, CEO of Broadpack, which is here, and also Jason Roos, Manager Strategic Growth and Ventures with Tayo, which is already at the jury panel. Also, I would like to thank you, our sponsor, Rapidus. It happens to be my employer. We are really excited. We are also a big startup, but very excited to sponsor this session. So please roll the video.
Rapidus was formed on August 22nd, 2022 to manufacture the most advanced 2-nanometer semiconductors. We are also facilitating the research and development of new and advanced packaging techniques. Rapidus will produce semiconductors that contribute to the fulfillment, prosperity, and happiness of people's lives.
Thank you. Next presentation, please. We will start with the students' presentation, and we put the wrong presentation up. All right, the session structure. So the way this session is going to run, we'll start with the pitch. We have actually two competitions. We'll start with the students first, and then we'll continue with the startups. Every speaker will have 7 minutes for the presentation, followed by 3 minutes Q&A from the jury panel. Then we'll go into jury deliberation. At the same time, we'll have the opportunity to take also questions from the audience. Once the jury decided on the winning presentations from the student and startup, we will announce the awards. And then, as you can see, we have drinks here. So we will continue with networking. For questions, you can also use the app. So as I mentioned before, the Q&A with the audience will come later. But please feel free to use the app. You select this particular session, and then you go live, and you can enter your question. Or we also have the opportunity to use a microphone here, whichever it's easier for you. So the jury panel, I will invite Jason to introduce our distinguished jury panel members.
Thank you. We have Yvonne Loich from...
I cannot hear you.
It is. Okay. I have Yvonne Loich from Lamb Capital. We have Paul Pickering from Silica Catalyst, John Wee from Applied Materials, and then we have, Henry from Micron Ventures, Martin Pierick from Kitorocket, and YY Tan from Yule Group.
Okay. Thank you. Next, please. All right, so we will start with the student competition, and I would like to invite Chris Bailey, who's professor with State University of Arizona, to introduce our speakers.
Yes, so welcome everyone. I said to Rosalia that it's not the University of Arizona, it's Arizona State University, so you got it right, you got it right. Okay, great. I'd like to welcome our students to the platform who'd like to come up. So we have some exciting presentations from 3 teams. While the students are coming up to the stage, this competition started with 25 teams. There was 2 phases of looking at the work and looking for what we felt was the highest ranking work. So started with 25, and we're now down to 3. So each team is going to give a 7-minute presentation, and then we'll have 3 minutes Q&A with the jury. So I'd like to invite our first team member to the mic. This is Ole Bergman, who's going to give presentation number 5. So Ole, come up. Your slides are here. Okay, so you have 7 minutes. All right.
All right. Thank you for the brief introduction. Thanks for the opportunity of speaking here. I will talk about our work about AI-driven virtual thermal sensors for smart power modules. And the problem that we want to address is that for power modules, we want to monitor parameters of interest in real time. And how can we do that? We can use sensors, physical sensors. They are used nowadays, but they add complexity and cost to power modules. Another option would be to use models, such as FEM models, but FEM models are very slow to compute and not suitable for real-time monitoring. Also, they contain IP that companies are not willing to share with customers or competitors, of course. But yet, we want to monitor those parameters. And this desire of monitoring the temperature, I will today focus on temperature. This desire demands for reduced order models, such as artificial intelligence models. So what are we going to do about it? First of all, instead of physical sensors, we want to use virtual sensors. But first, what are virtual sensors? A virtual sensor can be any area or region in a FEM model where the temperature can be read out. And those areas or regions are usually regions where you cannot place a physical sensor, such as a junction of a die or MOSFET. What do we need for this virtual sensor technique? Well, we need a FEM model that is very precise, high fidelity, and validated. How can we then use this virtual sensor for real-time monitoring? Well, we want to use a reduced order model, such as an artificial intelligence model or an artificial neural network. And this model can compute very fast and can predict, based on an input and a feedback loop, our temperature. And we will use an FEM model to train our artificial neural network. And we created 3 scenarios to prove this technique. In the first scenario, we have an arbitrary input current, time series data, and we feed it to our FEM model and to an electrothermal model, and we create a temperature profile or temperatures at different locations as an output, be it at the physical sensor location or at the dies or the interposers. And with this output data, we are going to train our artificial neural network. And in our case, we use 70% of the total data for training and the other 30% for validating. And you can see the results here, that the predicted temperature by the AI model for die 1 and die 3 of this exemplary power module fits to the true temperature that was simulated by the FEM model very well in a very small margin of error. Now, let's go to the second scenario. We made it a bit more realistic. We added a little defect in the sinter layer of the die attach. This defect is about 2.5% of the total sinter area. And we simulate it again, and we see a slight shift in the FEM model output. The red line is where the defect becomes apparent. But we don't see a change in steady state temperature. And we use the same AI model as before and predicted the temperature again. And you can see that the prediction is still very exact. So that tells us that our AI model is not model dependent and that it can even account for small production variances, such that there's little variance in the sinter layer, or for degradation during lifetime, for example. In the third scenario, well, we now thought that the temperature profile that we saw even in scenario 1 looks very much like the current profile. So we thought maybe we can even only use the current for the AI model as an input, but we needed a bit more data. So we used the current and we used augmented data of the current. So in this case, the logarithm and the sinusoid. And we trained our model with this data again, and then predicted the temperature. And as you can see, our AI model is still capable of predicting the correct temperature within a small margin of error. It's about 1 degree centigrade, which is, I think, pretty good for this kind of real-time model. And it worked. So we can even use an AI model without the sensor input, without the temperature input, and only train it with current data and still get a temperature output. What are the benefits of this model? Well, we can use a virtual sensor to replace hardware and power modules, hardware that adds cost, adds complexity, and adds possible points of failure. Furthermore, our AI model can create a real-time monitoring tool. And these models can even be a business case for companies. You can sell them additionally to your power modules, to your customers, because they don't contain any critical IP. They are very fast in computing, and you can train your model for different use cases as well. So this opens up a new business opportunity where you can even, on the one side, you reduce the cost in the module because you're getting rid of the sensor and all the integration cost that comes with it. You reduce the complexity, plus you're selling a model instead. Lastly, I want to thank my colleagues Keivan and Alireza, who unfortunately cannot be here today, especially Alireza, who drove this work really well. And with that, I also want to thank you for listening.
Okay, well done. So that brings us now to 3 minutes of Q&A. And so for the jury to ask any questions they may have. Jury?
So the microphone is working. Thank you, Ole, for this nice presentation. I'm wondering, and maybe my question has already been answered. So you don't need a new FEM model for a new configuration, for a new chip, or you do?
I'm not sure if I understood it.
If you have a different configuration, like another PCB with other power electronics there, do you still have to model this to?
Yes. If you create a big difference, well, in this case, we only had a small difference, 2.5%. If you have a bigger difference or a different use case, you have to train your model accordingly. But the FEM simulation only has to run once.
Yeah. Okay. And my second question, because I saw that the small defect had no influence, and I'm wondering, is the model so robust, or does the defect don't do any change?
Well,
in the first place?
In fact, you saw a difference, and I mentioned that there is a small, or I hope I mentioned, there is a small difference in the transient behavior.
I didn't see it.
Maybe I go back. There is a tiny difference in the transient behaviors. You see that the dashed black line is slightly shifted and not completely overlaying the blue line as it was before the defect was introduced. So you see a slight change. Yeah.
Okay, thank you.
Okay. Hey, thanks for the presentation. I just have a clarification question here. So my understanding is we are trying to look for, say, temperature, right? But instead of inserting a temperature sensor, we measure current or voltage and use that as input to predict temperature. Is that correct?
For the AI model, yes.
Okay.
You use current, yes.
So then my guess is it depends on where you take those current measurements and how many data points you take, and that will impact your accuracy of temperature prediction. Is that correct?
Well, if you take the current, ideally the current is constant. It shouldn't change, right?
Okay.
If I get the question correct.
Oh, I understand. Yeah. So when you take the current, because I don't know what the circuitry is, so basically at one point you take that's why what I was asking. Yeah.
Well, it's a DC output. Is it? Oh.
Maybe you just quickly answer.
Okay, so if it's in DC output, the current at the DC output will be constant, and you can measure that and feed that to your model. Okay.
Understood. Thank you.
Great, thank you very much, Ole. So that was Ole Bergman, Technical University of Delft, team presentation. Okay, I'm delighted now to introduce our team from Georgia Tech. And this is Emmanuel Torres, Christian Molina, and Ramon Souza. Okay, all three of you presenting? Yes. Okay, go ahead. So yeah, it's up.
Thank you for the introduction. The topic of our talk today will be the smart design of advanced package systems through a linked FEA and Bayesian optimization framework. Every year at ECTC, we see the results of huge investments into advanced package architectures for chiplet integrations. In response to user demands for more and more efficient compute power, we expect these systems to become more complex over time. For instance, physically getting larger in order to accommodate more chiplets and more components. Not only that, we will also have to assess and integrate new materials and processes as they are developed. This puts the industry in a position where we will need to decide if and where and how we will build these new systems with more tools in our toolbox. The challenge that we foresee is the need to balance and manage the thermal, mechanical, electrical, and physical aspects of package design, taking into account this increased complexity. Existing design tools are really good at managing and analyzing and optimizing for these considerations independently, but they tend to poorly communicate with each other, and it's harder for integration teams to understand how decisions made by one of these teams will impact another one. In the context of the competition challenge, we wanted to propose and implement a tool that the industry can use to design the system as a whole with system reliability in mind. We know that as these systems become more complex, we'll have more materials, more layers, more power running through them, and this will enhance or aggravate reliability concerns and failure mechanisms at every level of the package. This is a challenge that needs to be addressed holistically and with a robust understanding of the trade-offs associated with this multi-physics and multi-scale design space.
So to solve this challenge, we implemented Bayesian optimization framework that is built on open source libraries, and it takes the FEA solver as the black box function to be optimized. The first key benefit of this approach is that it considers not just continuous variables as input, but also categorical variables. Now, this allows us to streamline the optimization process since we don't have to optimize each category individually, and now the algorithm will determine which category combination works best to get the optimal solution. Now we feed these inputs into the FEA solver of choice, where the user can extract, evaluate the desired objectives to be optimized, and they're fed back into the optimization loop. Now, the second key benefit of this approach is that the BO, the Bayesian optimization, will create a probability function that will select the input combination that has the highest probability of being in that input space. After we finish the loop, we get a trained model that describes the behavior of this Pareto front or the solution space, where we can further use high dimensionality visualization tools to observe trade-offs between the parameters. Now, as a case study implementation, we optimize a large substrate architecture where we analyze how the chip package interactions are affected by changing the various parameters that the design parameters of a package. That this can include the different layers in the thickness, the layered materials, and BGA parameters. Now, for this specific case, we started with the core and device thickness, also the BGA pitch and size, and the material of the core. Now, we feed inputs into the FEA, where we got the plastic strain per cycle for both solder joints at the chip and board level, the package warpage and reflow, and the overall package thickness. These outputs are fed back into the optimization loop, where we train the model, and lastly, we get the optimal solution that we can furthermore reduce by filtering out depending on BGA life and yield criteria.
When we're talking about like the results that we're going to get, we're talking about the solution space. I want to emphasize that this is not a parametric study. This is a guidance, a smart selecting guidance to get the optimal solution. So when you're doing that, you can run out, you can like analyze your parameters, and you can get to know intuitive relationships between your inputs and your outputs. As we can see here, one of the figures that we can have in our results is the pairwise objective Pareto. So we have the BGA plastic strain and the warpage, and we can see, like, we can filter in based on the yield criteria that you have to have the optimal solution for your process. Another result that we can get is the Pearson correlationship or the Spellman. This one that we have here is the Pearson correlationship. It will tell you like what linear relationship you have between your inputs and your outputs, and will tell you how it's affecting one to the other one. So you can make like a design choice between like which parameter are you going to change. So the last one we can get is a high dimensionality Pareto, is when you see all your objectives. And this way you can see how your solution is like more how balanced the objectives are with your solution. So you can filter out whatever your like objectives is, and the more balanced solution will be in the one in the center. So we know that this is scalability and flexibility. We know that we can like accelerate the process design for screening materials, new architecture. We also know that the application, this is open source code that we can use to any FEA, and that way we can apply it to any of the thermal, electrical, or mechanical systems. As we do in our lab, we try to solve all the reliability issues by using this, how we can see here, for all the problems that we have. I also want to thank our PhD advisor, Vanessa Smith, and NSF for like the award for like financing this research. Thank you.
Great, well done, team. That should bring us now to the 3 minutes. Questions from the jury. Go ahead.
Quick question here. I want to understand, with this optimization routine that you have, you said something about informing material development needs. I didn't understand the connection there.
So normally when you're doing a simulation and you're changing your materials, that you like consider that as a category parameter, and you have to solve all your design space by using that categorical. By doing this, we can implement like a couple of materials as categorical, and because it's running as a continuous parameters, we can like keep in a single optimization, like differentiating which material is better for the same architecture.
Sorry, I have a loud voice. For solving relatively challenging data sets, what type of runtimes were you seeing with the tool?
So for this problem that we're running, even if it's 2D, the most like time consumption is gonna be about how your FEA is gonna run because the initial data is gonna be like believing for that. For this one, we run 80 runs, 20 for training and 60 for optimization. So that way we can like find the solution space. So that gives us like around like 60 hours.
And adding to this question, how does this compare with existing solutions? Because there are existing off-the-shelf multi-physics simulation tools.
Yeah, I mean, I would say the main benefit of this is that other methods, you need to create a surrogate model that could be in like neural networks that are pretty common, but that needs to explore the entire design space. And then you use some genetic algorithm or other optimization algorithm to evaluate that neural network to get an optimal space. But to get to that point, you need to explore the whole design point and perform expensive FEA simulations to get that. But this method, it's a more guided approach. And while it is performing the FEA simulations, it's looking toward that optimal space.
And is it because you are constraining your model with like physical boundaries?
Yeah,
physics constraint that's also existing, I think.
This guidance comes, and it's mostly from the Bayesian optimization, how it is built. So after every iteration, it trains a Gaussian process machine learning model where you can create something that's called the acquisition function. It's a probabilistic function that you need to maximize, and that will tell you what inputs has the highest probability to minimize or maximize your objective depending on where you're going. So every iteration, it will look towards the point that it thinks has the best probability of being optimal.
Great, okay. Thank you. The 3 minutes are up for Q&A. Well done. Excellent. Okay, so that brings us to our Team 3 presentation. This would be presentation 7. I think it's up on the screen. Yeah. So this is a joint presentation. Akshay Panchwaj who's doing a PhD at Chemnitz University, and Darshan Bakur, who's currently pursuing a PhD at Technical University of Dresden, but both working in collaboration with Bosch. So please go ahead.
Thank you. So my name is Akshay Panchwaj, and together with my colleague Darshan, today we will explain through a pitch how we reduce thermal mismatch effects through intelligent optimization of a power package and how this methodology as a whole is beneficial for the industry. So I'll directly start with the problem statement over here. So regardless of whether which industry you're working on or whether you're trying to bring your product or service to the market, what is the most important thing that you need is the fact that it needs to have a robust design. But in order to have a robust design, you need to have both time and money invested into it. But in today's competitive landscape, in order to have that competitive edge, companies wish to reduce their time needed to bring their product to the market and at the same time cut costs associated with it. So what exactly can be done over here to make sure that both the time and costs are reduced and at the same time you have a robust design? Well, the answer to that question is simulations. Simulations not only help you to validate your design in its early stages and thereby avoid any costly last-minute changes, but they also offer you a virtual environment to test your product in the environment it is intended to be used, which helps you to accelerate the development process. And last but not the least, it helps you to optimize designs upfront in the development process, which helps you to find that sweet spot between performances and costs. So what is our proposal over here? Well, our proposal is to combine physics-based simulations with AI-driven optimization in order to help the businesses make a smarter decision. But how exactly can this be done is something that we have tried to explain through the use case that we worked on as a part of this student challenge. So what we have over here is a very simple power package consisting of silicon chip at the top, a solder layer in between, and copper at the bottom. And this power package was subjected to extremities of temperature through thermal cycling, so extremely high and low temperatures. And the goal of that was to study the solder layer, because the solder layer is known to be the most critical component in the power package, and it's the life of solder, well, basically defines the life of the power package. And what we see over here on the right is not just a beautiful picture, but something that kills reliability, because that corner spot which we have highlighted is something, let's say, is a location where stresses and strains accumulate and ultimately leads to the failure of the solder layer. So the goal over here was to optimize the solder layer in such a way that we are able to reduce the stresses and strains over there, or as some person said, fix the middle child and everything all is fine. So how exactly we achieved that through methodology is something that my colleague Darshan will explain.
So start with, we do not do this classical brute force 1000 simulation, rather we do it much more smartly. So we have a Gaussian process model which actually learns on where to go. For our all AI ML engineers, towards the left side of the image, you can see how is the workflow process. First, we define the objective, and then from initial simulations, we train our surrogate model, and then, which is in our case, the Gaussian process model, and then we pass on this information to the Bayesian optimization, and then we update new parameters, and then redo this entire process again. But what's interesting and what's beautiful is in the right-hand side. We call that robot as Gaussian process robot, and it's very beautiful to say, because it actually guides, it not only learns the performance, but it actually guides the Bayesian optimization to choose the next right design point. And it also works simultaneously with this Pareto front over here, tries to make the best Pareto front so that we have the best trade-off between the stress and strain over here. So how about the results? So towards the left, we can see one of our simulations results. Here we can clearly see the best trade-off between the stress and strain. Actually, every dot over here is a success. Depending on the decision maker, it sometimes becomes problematic. So, but at the end, everyone is happy with choosing the right form of points over here. But we just do not give results, but we also say what caused these results through SHAP analysis. So we can clearly see through this SHAP analysis that what parameter actually affected these results. For example, maybe solder was actually influencing the solder thickness was actually influencing the stresses, or maybe not. So together combined, we can say that we just don't give results, our model just doesn't give results, but it also gives the insight and also the control. But Akshay, what do you think are the benefits here?
Yeah, I mean, it's not really hard to explain. So first and foremost, this methodology that we have over here is scalable and scriptable, meaning that it's completely flexible and it's not really restricted to just power packages, but it can be extended to any geometry that is out there. Secondly, it intelligently explores the design space algorithm. So when you compare it with traditional optimization methodologies, which might need 150 to 200 simulations in order to achieve conversions, this methodology does it in, like, for example, 30 simulations. So that means lesser core usage, lesser license costs, lesser manpower costs. So I mean, all in all, you're saving quite a lot of time behind one single simulation run. Thirdly, it gives a feature impact analysis. So like my colleague explained previously, through SHAP analysis, we understand how every single input parameter has an effect on the output. So for instance, if you have like 10 parameters on your input at the beginning, and you identify that there are 2 or 3 which have the highest impact on your desired output, you can focus your time and energy in solely optimizing those 2 or 3 parameters, and this can actually translate into savings in terms of time and money in the early stages of the project. And last but not least, this methodology that we have over here is based on open source software, so there are like no extra license costs associated with it. So depending on how integrated the complete optimization methodology is in your complete simulation workflow, it can translate up to, like, for example, 30% savings of your entire software simulation budget. So as next steps, it needs to be ensured that this workflow that we have over here is ready for the industry. And how can this be done is something, for example, through code review and benchmarking not only its performance, but also benchmarking it against legacy data. And last but not the least, validating its outputs on new test cases. And by saying money saved is money made, I would like to conclude our presentation today. And thank you all for your attention. And if there are any questions, please.
Okay, well done. That brings us to the 3 minutes Q&A. Please go.
Yeah, thanks for this very interesting presentation. Back to your last page about verification, I just want to understand whether you have some physical analysis done to confirm the die edge defect or through the simulation that you have. Yeah, this is probably another type of verification that you could consider.
Just to understand, you were asking us whether we have some physical model so that to validate or verify this, or?
Physical analysis like those SEM to check, the defect location and so on.
For this use case, we didn't, because we took out these results and verified it based on the literatures what we found. So we used the literature as a reference for us because of the challenge.
Question here, what is the scalability of this approach?
Scalability?
Yes, how can this scale to like larger problems or larger designs?
I mean, this whole methodology that we have over here is completely script-based. It's been developed in PyMAPDL, so it's a Python-based solver which is offered through ANSYS. So since it's completely script-based, it can literally be translated to any geometry. So like I said, it's not just restricted to power packages, but depending on the geometry you have, you can actually create your geometry in PyMAPDL through coding, and that's how it actually makes it scalable to like whatever product you have. So you can define the geometry, the mesh can be defined, boundary conditions and everything. It's something that you can define via coding in PyMAPDL.
One question, since you are doing this in cooperation with your employer, with Bosch, which I love to hear because I was at Bosch for 22 years, just to mention. Is the company, like your employer, willing to implement this in their own development tools?
Well, we are actually working something similar for our PhD work over here, and as it indirectly is like a digital twin, maybe in the future, yes, they would be also interested.
One last question here is there any matrix to show that comparing to existing tools, either how fast you can comparing to them or how much better you can do this? Because always it's measured by performance or efficiency.
Comparing with the full order model, you mean? Or
comparing to the alternative or existing approach? Because this question goes to the previous presentation as well. It really like how much faster? I mean, in terms of manpower or performance, silicon performance, how much, the PBA?
So I would say this is totally different, because ideally in your general cases, you do simulations, you gather the data, and then you train a model, and then you optimize probably. But this is like an entire package. So you don't do 1,000 simulations, you exactly do those precise 200 simulations, which can optimize your entire package in a more efficient way. So in terms of number of simulations and all the benefits, what you can see is the biggest comparison we can give now.
Great, thank you very much. So that brings us to a close of the presentations and the Q&A. I'd just like to thank our 3 teams. I think they've done a fantastic job. And just remember, we did start with 25. So these are the 3 finalists. So congratulations, everyone. Well done.
All right, thank you very much. So we would like to invite now the startup speakers. And the next presentation, please. All right, we had actually 11 applications, and after review, we decided to go with 5 startups, and we are really excited to have an international lineup of speakers. So I would like, just very quickly to introduce, we have Sanjeev Agarwala from Euclid, CEO of Euclid from USA. We have David Morris, CEO of ICSPI, coming from Canada. Adrian Lopez Vasquez, Head of Product Development from Micro Quasar Technologies, coming from Germany. We have Juniali Nauriyal, CEO of Photonnect Interconnect Solutions from USA, and Patrick Heisler, CEO of Scrona, coming from Switzerland. And now we are starting with the presentation, so please, next presentation, Euclid. And I will invite Farhan to.
So thank you, Rosalia, for the intro and setup. And with that, I would like to invite Sanjeev Agarwala from Euclid to the podium. Sanjeev, please come over. Thank you. Please go.
Thank you. So I'll be talking about what our Euclid is up to. Basically, overall, we are looking to revolutionize 3D metrology for semiconductors using quantum sensors. So overall, the world of semiconductors, both at silicon and package level, is going 3-dimensional. And effectively, that's where the next order of magnitude scaling is going to come from. And we see that happening all over across the industry, and really this is going to grow at a very, very high compounded rate. We overall expect the revenue of 2.5D 3D products to cross $500 billion by 2028. And one of the key aspects happening both at package and silicon level, so although there is silicon with backside also going 3D, I'm primarily going to focus today, as our company is focused today on packaging, but from an application point of view, we can cover this for silicon and even an adjacent market in terms of batteries. In the world of packages, particularly the interconnect scaling, particularly with microbumps and hybrid bonding, is the effectively new back end of line in advanced packaging, which will allow us to continue to scale packaging over next decades. But overall, in terms of really the reliable manufacturing of this advanced packages, today there is no inline tool post-bonding before final test at electrical. So you have optical in the beginning at a pre-bonding stage, optical, AFM, etc., and then you have final electrical test, but nothing in the middle. There are 3D techniques like X-ray and acoustic and others, but they can be done more from a failure analysis point of view, but from an inline application, one is they're slow, and second is potential damage, especially to memories. And so this is leading to a significant yield loss today, and really, especially as we continue to scale the interconnect, this is going to become a bigger problem over time. So that's where Euclid comes in. So we are developing what we call a quantum MRI platform. We call it QMRI, which is safe, fast, and can be used for inline inspection. Overall, what we are doing is we are using the quantum defects, or what we call the NVISA spin states in CVD-grown diamonds, which are ultra-sensitive to magnetic fields, and we can effectively transduce these magnetic fields to optical images, which we can transduce on a camera and capture any small sub-nanotesla, even picotesla level changes down to hundreds of microns buried inside silicon. And along with that, we have developed another proprietary technology, what we call electromagnetic excitation system. Since when we are doing this inline inspection, there is no current flowing, so to speak, because you are just stacking in a 2.5D, 3D silicon or in an interposer or HBM stacks, etc. So we have a mechanism of what we call, we excite the currents using eddy current excitation system. And we can be able to detect any small differentials caused by any kind of defects, whether they're open, short, or non-wet defects. And both of these technologies, we have a number of patents we have filed where we have a unique solution in the industry as we speak today. And in addition to that, we leverage the AI-driven defect classification, because really it's a function of being able to, as we do and more, we can learn and be able to see the exact defects, both in 2.5D and 3D dimensions. And our overall target is to be able to do 100% inline inspection up to a millimeter square depth, 1 micron resolution, up to 1 centimeter square per second. And the way QMRI works is because fundamentally magnetic fields are able to permeate silicon. And we are focused on measuring what we call the differential magnetic field. So think of a die or a wafer stack, whether it's a HBM or a logic memory stack, and you get a certain differential magnetic field signature based on a good die. Anytime there is any kind of defect in any of the layers of a stack, whether it's a non-wet defect down to a micron level crack or an open or a short, it creates a differential magnetic field signature which we can capture and be able to exactly tell there is a go, no-go with respect to good or a bad die. When we are doing inline, we are not necessarily focused on telling the exact location, but we can tell a good or a bad die. Overall, from a competitive point of view, optical, as I said, is really more at a planar level. Electrical is at final test, while X-ray is trying to make inroad, but primarily for failure analysis because it is slow and causes damage. So QMRI overall, we believe, is the only solution out there which can over time solve the 3D metrology problem. From a business opportunity point of view, like I was mentioning earlier, 2025, the revenue of 2.5D 3D market is close to about 220 billion, about 26 timeframe, about 300 billion. And if you look at just a 10% yield improvement if we can do, and we look at the Euclid SAM in terms of just doing really 2 insertion points per process step, it's about $1 billion serviceable market. So, and if we are able to offer a $30 billion revenue saving or improvement in overall revenues, it offers a significant return on investment for inserting these tools for inline metrology. We have built a number of partnerships over the years, and we continue to expand this as we go further. And like I mentioned earlier, batteries also is turning out to be a significant opportunity. We have a lab tool which we have been selling mainly for academic purposes. And what we have today in our labs are a benchtop unit which we are doing for wafer, package, and board level inspections. And our goal is to offer a nearline or an inline tool in 2027 timeframe. And finally, I think overall, we have a team of physicists and people who co-invented or invented this quantum sensing technology at Harvard. And overall, we believe we have a great team, technology, and a business opportunity to go after. Thank you.
Well, thank you, Sanjeev, for the great presentation. We're going to open to the judges. Any questions?
Yeah, great presentation. Thank you. Question about the 3D metrology. I can understand you use this MV center sensor to identify where you have a sort of a disconnection in a 2D. How do you identify where is it in the stack?
So the spin sensors actually have a Z state also. So there is a aspect of, in terms of the magnetic fields, because it's a cumulative magnetic field. So what we are looking is a differential. So for example, if you have, let's say, 8-layer HBM stack, and the defect is on the layer 7. So when the differential of that magnetic field is the total cumulative when we are looking from the top, and let's say the defect next time is on the layer 2, the 2 magnetic cumulative, what we measure at the top, are different. And over time, exactly what we do is we do feed-forward modeling, and we can tell exactly whether this was on layer 7 or layer 2 of the interconnect stack. So overall, the cumulative differential is what we are looking for. And that's what knowledge we can leverage to tell exactly where in the stack, whether it's a 2.5D or 3D, the non-wet or open shot defects are.
In inline metrology like that, speed is needed. Is this what type of time are for inspection?
So like I mentioned today, actually one of the companies on the jury panel, their lead business people were asking us, can you do 1 millimeter square per second? Our goal is 1 centimeter square per second. Actually, they were saying 1 millimeter square per 10 seconds. And what we are shooting for is 1 centimeter square per second.
Okay. And the target is 3D packaging initially, but do you envision this also for large form factor wafer, inspection?
We are actually working on backside power also as we speak with one of the, obviously, the pioneers in this. It's equally applicable there, but as a startup, we are focusing on one. And like I mentioned, batteries. So one of the companies we're working with is Honda Research. And batteries have a similar huge problem, if not a bigger problem.
Can you also distinguish between like not just an open, but like an intermittent, like a almost open, you know what I mean?
Non-wet defects down to a micron level. So cracks, for example, when you're, especially as you get into hybrid bonding and all. In fact, one of the speakers will be talking about that. So this becomes a very, very critical issue because of the dies are becoming thinner, you're stacking more die, the mechanical stress, getting the planarity right, and all non-wet defects will become a huge problem for advanced packages.
Okay. Yeah. Is your technology ready for panel level packaging?
That's correct. Yes, we do full wafer level because we can do 5 by 5 millimeter square, so we can pretty much cover the entire die, entire wafer.
Well, thank you, Sanjeev, again for the great talk. Thank you. Let's welcome. Okay. With that, I would like to invite David Morris from IC Spy. David, please come over.
Got it, right. Yeah, you got it. You got it. Thank you. Thanks, everyone, for being here again. Yeah, my name is David Morris from IC Spy. We make scalable atom-level metrology and inspection tools for the semiconductor industry to control defects and extend Moore's Law. So chip makers are flying blind. Today, something as small as 1 nanometer, the same size as DNA, can cause a defect. And that's a problem because there are very few tools that can see a nanometer and none that can see it at fab speed. So chip makers, they want to see something like the full picture. So they want to see something like this. But they're forced to make a trade-off at high resolution. Instead, they sample, so they see something like this. That's a problem because defects are not caught, wafers are scrapped, products don't ship on time, and you don't have sufficient yield to meet customer demand. To give you an example, one of the techniques that can see a nanometer is AFM, or atomic force microscopy. If you wanted to scan a wafer, it would take you about 70 years to do it. It's just one wafer. We've come up with a solution that overcomes this trade-off, delivering high resolution at high speed. What you're looking at is a 1 square millimeter atomic force microscope on a chip. It is 1 million times smaller than a traditional AFM. We call this technology micro AFM and have multiple patents and patents pending on the technology. What you can do is operate 10, 100, 1,000, or 10,000 of these micro AFM devices in parallel to boost the speed and throughput of collecting that data across your wafer by orders of magnitude. So you're able to catch those atom-level defects at scale. So this technology might seem like science fiction, but it is proven. We have bootstrapped an entire profitable scientific instruments business with hundreds of instruments around the world that use this technology, and it's used every day by scientists and engineers for quality control and R&D. We've also developed a robust supply chain for manufacturing these MEMS devices at scale. Our vision is to build 300 millimeter fully automated tools that harness the technology at its core to take wafer scanning from 70 years to a matter of hours, instead of sparse sampling to full wafer, and to really boost the productivity of high-value fab real estate, ultimately to boost yield. Now, yield, just a 1% yield improvement is worth billions to the industry in terms of avoided scrap wafers, but also has enormous environmental benefits because chip making is so resource intensive. One of those processes that needs fast AFM is hybrid bonding. So we're stacking wafers together, and you need to have sub-nanometer control across your wafer, and you need a way to measure that sub-nanometer control. So AFM is the gold standard for this, but it's just too slow, until now. In February, we published our breakthrough work in collaboration with IMEC, where we unveiled the world's first 10-site AFM system using our technology, where we were able to grab, collect that sub-nanometer data across the wafer to tell you if your bonding process is going to fail or not. So we were able to collect that data 10 times faster than is possible today. And that's just the beginning. In the past, we've done 4 scan heads on a fine pitch. I just showed you the 10 scan heads, and our roadmap extends to do full wafer, full die map inspection, and eventually 1,000+ full wafer map. In terms of the market, hybrid bonding is our beachhead market, which we estimate to be about a $230 million SAM by 2030. That's made up of these variables. I'm not able to disclose those variables here, but if you're an investor and are interested, please reach out. And beyond hybrid bonding, just within semiconductor, both the front end and back end, there are multiple applications as well as market drivers towards better and better metrology with feature scaling. And similarly, even in general manufacturing, there's a trend towards smaller and smaller feature sizes within multiple high-growth industries where just better metrology is needed. And we have the right technology for that. If we compare across different types of technology, one way to compare speed is through the number of measurement cycles you can accomplish in an hour. Our competitors, they can top out at about 1,000 measurement sites per hour, and our roadmap extends to 10 million. The reason that we're able to do that is just everything about the technology has been built with scale in mind when it comes to this tiny footprint, the fact that there's integrated electronics on that chip, and all the scanning and sensing is also happening on the MEMS device. And we have the right team to do it. I myself, as CEO, have 7 years of experience with precision systems design, semiconductor manufacturing, and sales. And everything you've seen here, we've done with a team of less than 10 people with no outside capital. So thank you very much. This is our vision for the future of semiconductor metrology and inspection. Again, David Morris from IC Spy.
Thank you, David. Yeah. Well, thank you, David, for the great presentation. We're going to open to the judges for questions.
Thank you for the presentation. Quick question about your AFM. If I understand you correctly, you're basically building AFM on a MEMS.
Correct.
And is your AFM needle still the same size as the normal AFM needle?
Yeah, that can be customized. Yeah. So it's anything that's commercially available today, we can do.
And if I remember correctly, I mean, one of the challenge for AFM is really just isolating sort of a environmental, any kind of a vibration or noise will throw your measurement off. And when you're talking about tens or thousands of these little AFM, how do you manage that part of the issue?
So the vibration itself, like just environmental noise, is much less of a problem because the system is so small. So the scanners themselves are not affected as much. They tend to naturally reject any vibrations. But I think maybe your question is more about crosstalk between those devices, especially when they're close by. So I went through it really quickly, but on the roadmap slide, there was one SEM image of having 4 devices. They were on monolithic silicon. And we've solved the crosstalk problems.
Great presentation. I'm a MEMS guy, so I love to see stuff like this. And The question I have is on the robustness. It looks like a bit of a delicate device, and is it really planned as a consumable? What's the longevity of the device?
Yeah, it's definitely a consumable. I mean, it just like any AFM probe, there's a probe on it as well that's going to wear out. So it is considered a consumable.
And can this be done cost effectively? I mean, the cost of an AFM tip is pretty cheap. This looks like a fairly complex device to fabricate.
Yeah, that's a good question. So there's some advantages without getting too much into technical detail, but what it comes down to is lifetime for the probe, right? And so if you're able to have much higher lifetime where if it's absent of the MEMS, so let's just say that the MEMS are more robust than the probe tip, it doesn't really matter that much. You can repair the probe. I guess the thing that I was trying to get at is if you can boost lifetime, which we can, so we have exquisite control over the probe, and you might notice as a MEMS guy that the stiffness of that cantilever it's very compliant. So actually the force that's acting on the sample, the probe sample force is very low, about 500 times lower than a traditional system.
Thank you, David, for your presentation. Can I ask one more question?
Very quick.
What is the biggest challenge you are seeing for scaling from 10 systems to 1,000 systems?
10 to 1,000? So that's a great question. 10 to 100, clear roadmap. Going to 1,000 is different. It actually comes down to probably packaging, right? And how do you do that for the arrays? So far, we've done arrays up to 4, but you have to make decisions. There's always going to be trade-offs with how large an array do you do when you have 1,000. Yeah.
Well, thank you so much, David.
Thank you.
Thank you. Thank you so much. Okay. With that, I would like to invite our next speaker, Adrian Lopez Vasquez from Macro Quasar Technologies. Adrian, please come.
Imagine being able to do Imagine being able to do Imagine being able to do surface modification without vacuum, no mask, and with greater efficiency. Hi, I'm Adrian from Microquasar Technologies. And the next generation devices of electronics, semiconductors, and photonics rely on heterogeneous integration, which at the same time depends on effective surface modification. For these traditional approaches like wet chemistry and with adhesives are imprecise, slow, and toxic. In the other end, plasmas have shown useful for surface treatment. However, they rely on vacuum, and that's imprecise and not efficient with a lot of material waste. So the challenge is clear. How can you enable selective surface treatment of micrometric areas using plasmas with no vacuum, no masks, lower temperature, and greater efficiency? Well, the answer is with tiny plasmas at atmospheric pressure, like the one you see in the image. We have been working in the last 6 years in a new direct writing plasma printing technology. At Microquasar, we develop advanced plasma printing systems to drive innovation in microfabrication and solve the challenges of heterogeneous integration. Our technology, developed at the Leibniz Institute for Plasma Science and Technology, enable high-resolution surface modification for advanced manufacturing and prototyping. In Microquasar, we have created a state-of-the-art patent-pending plasma source. We call it Microquasar. It allows you to do direct writing without masks, no counter electrodes, no shape electrodes, And that's why we can treat multiple materials, conductive and non-conductive. Our technology is fast, sustainable, scalable, and modular. But the most important is the resolution we have reached, starting at 35 micrometers, which is at least 4 to 80 times finer than similar plasma solutions in the market. With microquasar, we can do activation, thin film deposition, fine cleaning, and etching in 2D, 2.5D, and 3D, supporting gradients, complex patterns, and a multiple of different coatings across applications. Our journey starts in 2019 when we see the need of industrial plasma solutions. Since then, we have been recognized with different awards. We have received grants. We have applied for patents. We continue the development. We have launched active pilots with different customers and academia, and we held active conversations with several customers. We planned our official market launch during the year, continuing with the development for high resolution and also new cases. Max is one of our early customers. He has been using our device with great success, and he told us we have been looking for something like this for so long. The feedback has been really good. In terms of market, we can do more than in the market of electronics, from land sciences to photonics, even aerospace, wherever microfabrication and surface modification is needed. Microquasar sits at the intersection of 3 different markets: microfabrication, heterogeneous integration, and ultra-thin films. And as you can see, these represent a plus 20 billion euro market. So it's a great opportunity for us. And since we are a manufacturing tool, our relevance extends far across these markets. In terms of competition, we have high resolutions that other plasma jets, but we can do more than simple activation. We use less gas and less power. And when we compare with other technologies like ALD, we can process certain materials at higher resolutions, at lower temperatures, and much faster. In terms of business model, we are, of course, a B2B company. We can sell novel plasma solutions, custom engineering solutions for system integration, and also consumables for recurring revenue. For the financial projection, our prices depends on the application. So it depends on requirements and customization. And we expect 20 to 25 times profit on material and production for just the plasma source because of our production strategy, and 4 to 10 times for the plasma printer. We expect a revenue of 50K by launching our minimum viable product and securing our first customers, then 250K in the second year by launching our production printer and acquiring 10 customers. And then in the third year, we expect to reach 1 million euro by securing major contracts with larger companies and expanding to new markets and applications. I'm Adrian, co-founder and head of engineering. I'm part of a brilliant team led by Dr. Laura Valerias Mora, a scientist and engineer, and also Jasper is in the business side. And we are ready to bring our technology to the market. Let's build the future one plasma discharge at a time. If you want to see one sample or have some questions, we can reach.
Well, thank you, Adrian, for the great presentation. We're going to open to judges for any questions.
Thanks for the presentation. I'm just curious, for this product, you're going to target for like a mass production or prototyping R&D kind of use cases?
So we started in another industry. First, we started in the biological sector. So we started with low volumes, but we see some future in this area of electronics, so we can also scale, but it's mostly for prototypes and all of that, because we cannot compare with other types of technologies. Sorry.
So just to make sure I follow, so you can still target for prototyping, not mass production?
Yeah, we can also scale to mass production because we can put different heads, and also it's very modular, our device.
What is the throughput needed for mass production use case?
The what, sorry?
What's the throughput How fast you can print.
So we can do.
No, it's not what you can do. What's needed for mass production, you think?
I think basically investment at the end. So our devices, we can mod a lot in series, so it's not a problem. It's more of trying to control all the devices and see what is the speed and all of that stuff. Yeah.
Thank you for a good presentation. You talked about a lot of the different market different market applications.
Yeah.
Do you have a specific focus in terms of, you know, you're talking about 25K, 250K million in revenue for the first 3 years. You have a lot of different markets. Do you have a strategy about what markets you go after first and where your biggest opportunities lie from a larger revenue opportunity?
So I think the primary market will be, we start, as I told you, in the biosensor area. So that's where we start. But also from the electronic side, I think what is more needed right now is for activation. But as I told you, we can do more than that. So there's companies that are interested in our technology to use it like a competition of ALD or so it's basically a tool. Yeah, it depends on your needs.
Do you have an estimate of your market opportunity specifically in this area of the industry, advanced packaging, activation you were talking about?
Yeah, for example, I told about Max. He's using it for creating scaffolds for growing eardrums. So basically, it can be do for everything. So we can do polymers, we can do metal oxide. So really, it's a tool, basically.
You mentioned about 35 micron resolution.
Yeah.
So do you have any innovations in the pipeline to achieve smaller capability?
Yeah, we are trying to stay in the micrometric area because that's why we try to aim. We cannot get lower because of physical limitations, but we see a niche in that area. So I'd say I would like to say we want to reach to at least 10 microns.
Thank you so much. Thank you. Well, thank you, Adrian, again for the great talk. Okay, so that brings me to our next speaker. I would like to invite Juniali Nuriel from PhotoConnect to present.
Good evening, everyone. I'm Juniali, the co-founder and CEO of PhotoConnect. At PhotoConnect, we are providing this new technology to connect optical fibers to photonic chips. You might wonder where exactly we are using these photonic chips, and especially at a conference like ECTC, everybody knows so there are about 5,300 data centers just in the US itself. And each data center has 100,000 of optical transceivers that are transmitting your information from one place to the other. This is where we are using electronics and photonics together to combine and use best of the both worlds. This is how a transceiver looks like, but it is predicted that over $46 billion will be spent in the US photonic packaging market. And that is a huge number. One of the biggest reasons is that when you connect or you bring fibers to these chips, it can cost up to 40% just in terms of packaging and testing. And let's see how they do it currently. So you would have an optical fiber as thin as a single strand of a human hair that transfers your information to a photonic chip or a photonic IC. Currently, everybody relies on gluing these two together. Imagine gluing two pieces of hair together. And these are going in data centers. This is highly unstable. It takes up to 10 minutes, even in a process line, to cure them. So it increases your cost and decreases your performance. At PhotoConnect, we use the same optical fiber, but we first introduce our patented mode converter design technology that will help in increasing the efficiency of your connection, so reduces loss, and these are going in data centers. This technology is protected by 4 patents, out of which 3 have been granted. Then instead of gluing them together, we use a laser to fuse the fiber directly to the chip. This process takes less than a second, gives you increased throughput, and will reduce your losses significantly. So the market that we are getting into is the global photonic integrated circuits market, which is growing around 21% annually. By 2030, the market would be around $46 billion US dollars. And from that total market, the market that Photonic can reach in terms of SAM would be around 2.8 billion US dollars with the way we would be selling our equipment into it. So a little bit more about what we do in our mode converters is that this technology would be partnered with foundries, and customers can directly use it as a design service. But this gives you lower losses at your junction with less than a dB coupling per facet insertion losses. Secondly, the laser attach machine would be increasing your manufacturing throughput, thereby reducing the cost of each of your devices by at least 50%, and then can scale up your manufacturing needs significantly. In terms of our competitive advantage, we are the only company in the industry right now that relies on laser fusion to connect optical fibers to integrated photonic chips. Thereby, we are the fastest in the market as compared to epoxy dispensing or using photonic wire bondings or other techniques. But we also have our mode converter technology that gives you a boost in your signal performance, thereby reducing the signal losses at the junction and providing you with the best losses in the industry and the best cost savings. So a revenue model has 3 parts. First, which we are currently doing, is providing packaging and design as a service, where customers can bring in their chips to us. We do fiber attach as a service, and they pay per connection. Secondly, as they start to scale up, we would be selling a modular unit, which is our PIX attach machine that can go in existing machines or a standalone unit. And because we're selling an equipment which would have a software IP, we would also have maintenance contracts that would help generate recurring revenue. So why would anybody switch? This is pretty simple. If you are producing 2 million units a year, you would need at least 38 of these machines. But if you switch to Photonic, you would just need 5 machines, and that is around $33 million just in CapEx savings. So till now, in terms of company traction, we have done 15 paid pilots, generated more than $150,000 in revenue from sales, $1 million in non-dilutive from government grants, and $500,000 in pre-seed funding. So revenue is predicted to increase over the next 5 years as we see the service customers convert into actual machine buyers, and then, which would be our benchtop systems, and from benchtop systems, we would be selling into a bigger, fully automated machine that can go into process lines. So our team has more than 100 years of total overall experience. We have 4 full-time employees, and we have a strong advisory board with technical as well as business background. So we are currently fundraising, but we are looking to launch our first ever laser attached machine in the market by early next year. We provide the lowest losses, and because we are reducing the loss in each transceiver, you would see energy savings on the overall data centers plus cost savings. So we are Photonic. We provide the connection that optics needs, but we can do for a fiber attach in less than a second, as well as reduced insertion losses and your cost savings. And thank you.
Thank you so much for the great talk. We're going to open to the judges for any question.
Yeah, thank you for the presentation. I want to understand a little bit. You said you showed that you have a significantly lower signal loss. Is that the result of using this mode converter And to be honest, I didn't quite understand what the mode converter is doing.
Yes, that's a great question. The mode converter is, it's a part of your chip design that would match, so that would help in matching the mode between your optical fiber and your waveguides that are in your chip. Right now, you would not have that, so you would directly get a waveguide and connect it to a fiber. But when you do that, you have extra losses just because a waveguide has a mode of around 2 to 4 micron square, whereas your fiber has a mode of 10.4 micron. So there's a lot of mode mismatch, and this helps in matching the modes better so you can get reduced losses.
So then as a follow-up question, is it the mode converter that is solving most of the problem, or is it that you're getting rid of this glue, which looks like, you know, in comparison, very unprofessional to what you are doing?
So both of them lead to reduced losses. If we are talking about mode converter, that would give you reduced losses to less than a dB, and but using, let's say, so that does give you lower losses. Now let's talk about the laser fusion process. Let's say another company had a really fancy design of their chip which they don't want to change, and they're getting coupling losses of 0.5 dB. And when they use epoxy to make the connection, that loss actually goes up. So if they want to use the laser attach, their losses would either remain same, or you would see an improvement of 0.3 dB per facet, because you get rid of the back reflection, so it does give you better coupling efficiency in both ways.
Yeah, my question is this technology ready for edge coupling and also this grating coupling?
So this technology is currently for edge coupling, but it is compatible with grating coupling as well.
I have a question about the market size. I think one of the slides shows that you use the optical co-packaging as your benchmark and scale it down. But shouldn't we really look at this fiber attachment machine market size as the one? That's one thing consideration. And the other one is, I think the other slides shows that existing systems need like 38 machine, and with this great technology, you reduce it to 5. Then it leads me to think like ultimately how big the market is.
Yes, so that's a great question. I think we are, so we can target the fiber attached machine as the market, and those numbers currently are all over the place, but we took the photonic integrated circuit market, like that entire market, in the next 5 years, because that is significantly growing. It has AI and quantum and all these other included in it. So that's where the market numbers came from. And then secondly, you wanted to know about the market for the machines, right? Yeah, so the market for machines.
Because to me, that's the real market.
Yes. So the market for machine, it's growing significantly, and because, so yes, they can use 5 machines, but that also says that we can charge them a lot more to sell a single machine to have the same amount of ROI or revenue for us.
Okay. Well, thank you so much to Giuliani for the great talk. And so that brings me to our last speaker. I would like to welcome Patrick Heisler from Scrona to present. Patrick.
So, thank you, everybody, for staying here so late. I'm the one between you and beers, so let's make that fast. My name is Patrick Heisler. I'm the CEO of Scrona. We are here to revolutionize micromanufacturing. We heard a lot about that over the last few talks. You heard about MEMS production and how scalable that is, and about the different market sizes. I will show you market sizes again, so check the numbers if that's the same you've seen before. Micromanufacturing is a super important big topic. So it's at the essence manufacturing on the micrometer scale, which is at the heart of the brightest displays that we will see, the next and best and most sensitive microfluidic devices out there, the next generation of wearables, but also the next generation of AI chips. And we're going to power that with a printhead that you can see here, which brings printing to the 21st century. Why is that needed? Because current technologies are limiting the innovations that are possible in the micromanufacturing range. So if you look at current technologies, that's screen printing, inkjet printing, they can't reach the resolutions that are required for these products or for these chips. If you look at lithography-based systems, stepper systems, they require huge capex. By that, they limit the accessibility of the technology. They have huge technological challenges by using 22 and more steps for a single product, which again limit the designs that are necessary with very strict design packages that you get from the manufacturers. And last but not least, they have huge environmental impact because they're subtractive processes. So you add layers, you etch them away, you have to clean, you add more layers, which combined with the market growth is just a very bad trajectory for everybody here on that planet. So that's where we are coming in. We redefine printing. We redefine printing in the sense that we don't use a mechanical force to generate a drop, but we pull. Similar to a tractor beam, we pull the drop out and guide it to the surface. This concept is around since hundreds of years or 100 years. There's a company doing that, but what is really different from our approach is that we've put that in a highly scalable MEMS package that puts it into the regime of mass manufacturing. So we have this highly scalable MEMS package, and at the same time, this technology gives us 100 times more flexibility in terms of materials. We can print high viscosity materials, we can print fillers, we can print all kinds of materials that you could think of with a resolution down to 0.5 micron, which you see down in the corner, which is a conductive circuit printed in silver with out of a multi-nozzle printed with submicron resolution. So this really replaces these very complex manufacturing lines with two simple processes, printing and curing, which gives you a digital computer-defined manufacturing technology for mid-volume, mid-mix production, but also high-volume productions. It reduces the capex requirement significantly since you can get rid of a lot of the tools down in your tool chain, and it reduces the waste significantly because it's an additive manufacturing technology that only adds material where it's needed. So since this is a technical conference, I have a couple of examples here, high-resolution prints of conductive inks, RDLs, UWB antennas, but also adhesives with high viscosities up to 40 Pascal seconds. So that's really viscous. You turn it around, the glass around it, it will stay in there. We can print it with micrometer resolution. Huge markets. You've seen the market sizes before for micromanufacturing. That should overlap quite well here with the advanced packaging technologies here. We're also looking at display technology, display packaging, consumer electronics, but down the road also at defense tech, anti-counterfeiting technology, and life science applications. We've been around since 10 years. We've worked with universities around the globe over the last years. Since last year, we have the Gen 3 of that technology out in the market, which is the first time multi-nozzle EHD is available for high volume manufacturing on an operator level. We're now working on Gen 4, which makes it available to panel level packaging, and then working on high value application where we will provide the full solution, for example, for ceramic printing, dental replacements, and others that are a little bit of outside the scope of this conference. We're special in the sense that we're vertically integrated. We have software development, electronic development, and the microfluidic development in-house, and we're operating our own MEMS production line, which gives us a huge competitive edge. We have 10 days of circle time from design to testing in our own application labs, which we have in Zurich, but also in Taiwan, in Kaohsiung. We have an application lab with a tool there, being close to the semiconductor environment ecosystem. We're working with universities and research institutes across the globe, global machine manufacturers and material providers, but then also the OEMs and device manufacturers. We have more than 50 patents on the technology. The business model is that the printhead is a consumable. You have to replace it every few months to a year. It's recurring sales combined with software and licensing models on the technology. The integration kit is a one-off sales into the machine, and then we also have additional processing modules that help our customers to have better process control. This brings us to around $100 million in revenue by 2029. We have a huge market pull since the introduction of the Gen 3 mid of last year. Over the last years, we've sold around 1 system per year. We've sold 7 systems over the last 3 weeks. We have a forecast of around 20 systems for the remainder of the year. We have a very strong team with the founders, technology guys still in the company in leading roles in the development, plus experienced managers all ready to enhance the team, and a strong board with serial entrepreneurs and investors. Thank you.
Thank you, Patrick, for the great talk. Any question from judges?
The range of materials that you're able to dispense or to print, all kinds of metals, all kinds of polymers, it seems almost too good to be true. How much have you actually explored with the range of materials?
So we have explored quite a lot. Since the team is working on that technology since 15 years, they've worked with almost all kinds of materials, from graphene to biomolecules to water-based systems. So all kinds of stuff. The question is always, what can you really bring into high volume production, right? You need that liquid phase. Not everything can be run with the same frequency. We're typically looking at reaching 10 kilohertz in drop frequency out of a single nozzle. If you want to reach that with very high viscous materials, that's going to be a challenge, right?
Okay. I guess just follow up on that question. When you're looking at a new ink, how much of a design effort is it? Or do you have to tweak, and what are the levers you have for your printer?
So the printer is, or our MEMS process is running on a platform model where we can do customizations or ink adaptations very quickly. We have standards. We have a high-resolution standard printhead that works for inks somewhere in between 1 centipoise to 300 centipoise, maybe up to 1,000 centipoise in some cases. And then we have a high-viscosity printhead that goes up to around 40,000 centipoise. If we then talk to really high-value customer, high-value applications, we do customizations, obviously, that tweak the last bit out of the technology. But there's standards. So the universities typically use standard printheads for their development work.
How about over topology on the wafer itself? What's the tolerance there?
That's a very good question. So our patents, a lot of our patents are about that. So we separate the electric fields that we use to generate the drop in 2. So one electric field generates the drop, the second one guides it to the surface. So we are very insensitive to any topography on the surface because that is only a guidance field. So we typically have working distances of 500 micron to 1 millimeter. So any topography that's on the 100 micron scale typically doesn't impact the result. And we don't have to follow it, right? So we just stay at a certain position.
Okay. Well, let's thank you, Patrick. Thank you for the great talk. Okay, and that's going to end the startup presentation. I'll let you, Rosalia, take over.
All right, thank you. So now is the time for the jury to deliberate, to look over all the presentations and decide who the winners are. And during this time, everyone in the audience who would like to ask a question, either from the students or from the startups, you are more than welcome to do that.
Well, I've got a question about the fiber attach. I think that's interesting. So Please help me understand, when you say the fiber attached, do you mean directly on the surface of the die, or are you talking about the edge couple? Or what is the mode of the attachment, if you can talk? That's okay, you can talk. Yeah.
Yes. So right now, the fiber attach that we are doing is from the edge of your pick or your die. We can do it from the top, and it's directly connecting to your die. So it's a permanent attach. It's a glass-to-glass bond, and that's where you get rid of your back reflections, and you can do high power as well.
And then how many fiber at the same time? I mean, are we talking about a bundle of fiber or just one or two?
So we can do a single fiber or 20 fibers at the same time. So it'll take 1 second to do one fiber or 1 second to do 20 fibers.
I see. Okay, makes sense. Thank you.
All right, any other questions?
Good evening, everybody. I think everybody did a magnificent job. I have one specific question about the magnetic interrogation using the diamonds. I understand you might not be able to tell us very much about the diamonds, but what can you disclose about sourcing the diamonds, about the nature of the carbon itself? Do you require like a single crystalline, or has that been a big challenge for you guys to integrate that?
No, so I think we are using CVD-grown diamonds. Actually, that's becoming a big industry. So there are a number of companies. We worked with Element 6, which is owned by De Beers. And they're a billion-dollar company because there's a lot of industrial use of these CVD diamonds. And what we use is ensemble, basically, because they can control. So the diamond is grown CVD, and then they put in a plasma layer, they create what we call nitrogen vacancies. So we can precisely control where we place them and the level of, so to speak, nitrogen vacancy doping. And we can exactly make it to what we are looking for in terms of the sensitivity and all. So, and even they're manufacturable. These are because diamond carbon lattice is very, very stable. So from a lifetime or stability or operating in extreme environments, highly stable and commercially manufacturable. So quantum sensing actually, obviously you hear much like quantum computing and all, the use of this is very broad, and over next basically decade and all, we'll see a lot of these kind of sensors coming into market.
Very cool. Right. Any other questions? Also, we have the students, don't forget, yeah.
I'll ask one for the micro AFM. Yeah, I'm curious how you decided the high volume inspection is very challenging. I think a 10 by 1 array of micro cantilevers would have also a lot of applications for research.
Yep.
And you would definitely speed up AFM inspection and make it just as, probably lower risk, but very broad application. So how did you decide to gear the company towards more high volume manufacturing?
So, I mean, we still sell scientific instruments, right? So there is that. That is the business today. It's just, at the end of the day, scaling to, because the scalability, we can go up to 100, 1,000, 10,000. Ultimately, where can you really provide the most value? And so if you just look at the scrapped wafer, right? If you're able to boost that, 1% yield, it just ends up providing a lot more value. That's all.
Yeah. Thank you.
Yeah, question for Scrona. I wonder what you can say about the size of these droplets and about the speed.
Yeah, so the droplets are on the range of femtoliters, typically. Speed 100 meter per second when they hit the surface. It really depends on the electric field that we're applying between the wafer and the print head.
What approximate droplet diameter would you estimate? The size of the droplet, not the volume, the diameter?
The diameter when it hits the surface is depending on surface energy and all kinds of different dynamic parameters.
While it's flying through the air, what's the diameter approximately? Is it like less than a micron across?
In air, it's around micron size, yeah.
Okay.
can be micron to 5 micron.
Thanks.
So if that question goes to drop watchers, it's very hard to use drop watchers for these kind of systems. So we typically use bottom microscopes to observe the process.
All right, any other questions? I mean, if not, we can start the networking, and when the judges are coming, we can give out the awards. All right, thank you.
So Rosalia, do you want to come and speak over here? At least for now. Oh, really? Oh, we're going to do the board down there?
All right, we are ready to announce the winners, but first we would like to appreciate every speaker, so we have some small token of appreciation. So please come next to the ECTC board.
First for each of the teams? Do you really need this? Okay. So we would like to have Ole Bergman to come up first. Yeah. So here's appreciation. There's also one for each of your other teammates inside.
Awesome, thank you.
Okay.
Yeah.
And
maybe we get a picture.
Yeah. I think you all students together will be here until like morning. Okay. So we'd like to give out for Emmanuel, Roman, and Chris to come up here from Georgia Tech.
So, this is Ramon.
Yeah. Emmanuel and And then Akshay and Darshan. Okay. And then the actual winner is the team from Georgia Tech. We actually have three.
There is a free registration for next year at ECTC, so you're coming back.
For the next challenge?
For sure, Mike, you can come here.
Thank you. Oh, wait.
It's not the first time that you had this, yeah?
Emmanuel and I won.
Yeah.
Okay.
Congratulations again.
Yeah.
Yeah.
So,
We have And then this is
Okay.
the
Yeah. That's,
So I
Okay.
will be giving to him.
yeah. Yeah. Okay. Well. Okay. Okay.
It's
Actually,
here. It should be here.
I need the names.
Yeah, it's here.
David Moyes, I can do
Yeah. Okay. Okay. We'd like to give our special thanks for the startups as well. So. David Morris from iSpot.
All right, thank you.
Okay. And then we have Adrian to come up from Micro Quasar. Thank you. And then we have Junia Ali from Photo Connect. And then Patrick Heisler from Scrona. Okay, and then really close competition, pretty much a tie between two, and so the judges picked picked the final winner, which actually happens to be Patrick from Scrona.
Oh, yeah, I almost forgot. Okay, so, yeah.
Okay. Oh, yeah, you get the.
Yeah.
Not enough hands.
Yeah. So,
I might want to get in here.
so besides the flag, there is a marketing award, service award from Martin, and also from Yon. So that we don't have the certificate now, but also Yon will have a picture of
Yeah.
all about.
So, yeah. So can we grab everyone, jury and everything as one big picture?
And who got the flags? We also have the boxes.
Yeah.
So-
Carrie Q.
Yeah.
I only have Carrie's. Thank you.
You'll have to figure that one out. So all the startups, jury, everyone
Yeah.
involved, students?
Students?
Okay, I'm in the front.
Yeah.
You can look over there.
You might have to, I think you might want to. Thank you.